With that, I would like to introduce Nadia, who's a professor at UC San Diego, and my wonderful postdoc advisor. Some of you may know her from her starring role in many academia-centric viral videos, but she's also an amazing researcher. She's the winner of the Sloan Fellowship. She is just a pleasure to work with. And her work focuses on doing program synthesis by harnessing many different kinds of formal methods, all in order to make the lives of programmers easier, and on bringing program synthesis to other sciences outside of computer science, which is super cool. So over to you, Nadia.
All right, thanks for the wonderful introduction, Hila, and I'm super psyched to be here. And this talk will be what basically Elena and Hila asked me to talk about is just an overview of the field of program synthesis, which is, very exciting field that I work on. And so just for those of you who don't really know what program synthesis is about, the goal of program synthesis is to automate low-level details of programming so that we enable programmers to write software faster and with fewer errors. And the high-level idea is that we want to enable programmers to express their intent using more directly, sort of using high-level declarative specification, and then automatically translate this specification into an executable program. And the difference with between what a synthesizer does and what a compiler does is that the gap between the specification and the program is so large that you would have to use some kind of search. You search in a space of all candidate programs until you find one that fits the specification. And from this description, I think you probably already realize why program synthesis is such a fertile ground for the overlap of programming languages and HCI research, right? Because our goal is to make programmers' lives easier, is to invent this new next generation way for programmers to communicate their intent to the machine. And of course, we need expertise from the HCI researchers to know what programmers need and what is better for them. And we need the expertise from the PL researchers to figure out how to make it work, right? And yeah, so I'm really excited that the human-centric program synthesis is picking up pace definitely in recent years, and hopefully the new generation, you will take this baton and carry it forward and make this area even more awesome. So what are the main challenges in program synthesis? Well, all three parts here, the specification, the search, and the program space, are sort of the areas of research, right? How do we specify intent? How do we search efficiently? And how do we specify the program space as well? So in this talk, I will focus on these two, right? The intent specification and the search. And in particular, so what I heard from Elena and Hila is that in particular HCI folks might be familiar with some approaches to program synthesis, some ways of specifying intent and searching, but not others. So my main goal today is basically to give you this broad overview of other ways of doing these things that exist, right? So that you're not restricted in your research, and you can leverage all of these other cool parts of this field. Okay, so first focusing on the specification part, we have tried a lot of stuff in the synthesis community. So you might be familiar with specifying programs with input-output examples or demonstrations, but beyond that, you can also do it with a reference program, reference implementation. You can do it with formal logic. You can do it with types. You can do it with natural language and many other things. On the search side, I heard most HCI folks are familiar with version space algebras, but there are other ways to do search, like enumerative search, stochastic, constraint-based, and again, some others. So this talk will be organized in two parts. Basically, I will first introduce you to different ways of specifying intent. And I will do that using demos of some tools that are out there. And then I will talk about the search strategies. So let's start with the specifications in particular. So first, before we talk about the different kinds of specifications, let's discuss really briefly what makes a good specification for synthesis. And we will be viewing all these examples that I give you through this lens. Right? So we want the specification to be human friendly on the one hand. So we want it to be easier to write than the final program, because otherwise there's no point doing the synthesis in the first place. We also need the specification to be informative. And by that I mean, so we don't want it to have too much ambiguity, right? Otherwise the machine will not know what you mean. And on the other hand, we want it to be synthesizer friendly, right? Because as the synthesizer will be doing this search, which is a really hard problem, we want to help it, right? So we want the specification to be easy to check, and we want it to hopefully help us do the search, guide the search in some way. So let's see what I mean. Might seem a bit abstract right now, but let's see how we can view different kinds of given specs in this slide. Okay, so I will in particular go through 4 different specification languages: examples, programs, types, and natural language. I will focus, I will spend more time talking about types than about other things, because that is something that I'm most interested in and you probably least familiar with, but I will give you a quick overview of the other 3 as well. Okay, so let's start with programming by example, input-output examples as the specification. The most famous example of a synthesizer like that is FlashFill, right? So this FlashFill is basically known as the main commercial success of program synthesis. FlashFill is a tool inside Excel that helps you manipulate your data, right, in a very user-friendly way. So let me just, without further ado, give you a demo of what FlashFill is and what it does. So here I have a spreadsheet with names. So I have a column with names of some people, which has last name, comma, or first name. Let's say my goal is to extract the first names of these people from this list, right? So what choices do I have? I can either type in all these names by hand, right? But then I'll have to do a lot of typing. Maybe there's 1,000 people in the spreadsheet, I don't know. Or if I'm some kind of Excel wizard and I know all the formulas, then I can just type in the formula right here and, you know, extract the first name. But, you know, very few people can do that with the formulas. So Excel gives you the best of both worlds and solves this problem for you. Sorry, FlashFill, I mean. With FlashFill, I can simply type in one example of what it means to extract the first name, and then I click this FlashFill button, which is under data in Excel, and it automatically fills in the whole column for me, right? So, and by the way, maybe it didn't do exactly what I wanted, right? Because maybe I didn't want to extract everything but the last name, but I actually just wanted the first name. Well, then I can simply go and correct the ones that were incorrect, and then it will go and update everything, right? And now I actually got what I wanted, just the first names. So you might ask, you know, what does it have to do with program synthesis? It's just some like Excel magic, right? But the way this works under the hood is it's actually synthesizing an Excel formula, basically, that satisfies the input-output example that I gave it, and then runs it on the other rows, right? So this is what it has to do with program synthesis. So to quickly discuss what other tools are there and what domains programming by example and programming by demonstration is good for. So we have seen text transformations, right? So what we have seen is FlashFill, but there are other tools that are doing similar things. So for example, Flash Extract is a tool also from Microsoft for extracting structured data from semi-structured text. And by the way, I don't have links to all of these tools that I'm talking about right now in my slides, but I will put them in later, and hopefully when, you guys will probably put the slides online, right? So I will have all the links in there, I promise. Because I'm just throwing around the names of all these tools. So so these are tools that help you perform text transformation. Another popular domain for programming by example is web scraping. So there's a tool again from Microsoft called WebRelate. Then Sarah's work is obviously all in that, so mostly in that domain. Here, so the difference between programming by example and demonstration sort of comes in, right? So it's similar, but in programming by demonstration, you are the user is demonstrating a sequence of actions rather than simply giving one input and one output. So in data science, programming by example has been very successful. So there are tools like, so Morpheus from Ishal Dilek's group. This is less of a real tool out there, but more of a demonstration of an algorithm. But recently there was this very exciting work on Rex, a tool for data scientists that is integrated in Jupyter notebooks and allows you to do data cleaning tasks by example. And then the final domain is what I call like a programmer's assistant, right? So for lack of a better name, this is a problem where, you're sort of just programming along, but you might not know some APIs, or might not be familiar with the language. And then you need to solve a little programming task as part of programming, right? And then the synthesizer helps you figure out, oh, these are the library methods that you need to call to achieve this task. And some tools, some examples of tools that do that are Frangel, that I think was published at PL+, 19, and some recent work from Hila and myself and students from our group on Snippy. That's actually very exciting. You can check it out online. We integrated a synthesizer inside a live programming environment, and this provides a really neat interaction model where you can enter examples through the live programming interface and get little snippet codes back. Unfortunately, don't have time to show you all these tools. They're all super exciting, but again, I'll put the links in the talk. So what about strengths and limitations of this way of providing specifications? Well, definitely the selling point of programming by example is that it's beginner friendly, right? You don't need to know programming language. You're just putting in some input output examples. That's great. That's democratizing programming. So usually it's also easy to check if a program that if a candidate program satisfies input and output examples, you can just run it, right? So there's a little bit of an asterisk next to it because it means that you need to have a complete program if you want to run it and figure out if it satisfies the examples. But then PBE also has some disadvantages. Examples are ambiguous in the sense that they only specify what happens on particular inputs, but not on any other inputs, right? So if you're trying to synthesize a complex algorithm, you'll need a lot of examples to specify its behavior in sufficiently to restrict the search to the right program. So examples are great for some domains in the sense that if you're trying to specify a string to string transformation, that's great because you just type in a string, you type in another string. But if you think about wanting to specify some complicated data structure transformation, for example, you want to specify, you want to synthesize insertion to a red black tree, right? How do you write examples for that? So first of all, typing in a tree is quite a bit more complicated than typing in a string, but also if you actually want to provide a concrete output, you would have to know how exactly this red black tree insertion works to figure out what is the result of inserting a particular element into a particular tree, which is not always what you want. You don't always know exactly how the algorithm works to be able to provide an output example. Another limitation of examples is that they're good at specifying functional properties, right? So the input-output behavior, but what if we want to specify something about the program's security or its runtime, so its efficiency, right? All these non-functional properties out there, examples usually cannot specify those, right? So examples have their limitations as well. Okay, so enough about examples. Let me go to the next one, reference implementations, right? So here I will show you a demo of another synthesizer called Sketch. And let's say the program that we're trying to solve is, so we're working with bit vectors, bit vector manipulations, right? And what we're trying to do is isolate the least significant 0 bit in a word. So for example, if we have this orange word here on the right, the least significant 0 bit is this 0, you know, the second last 0. And so isolate means we want to return another bit vector where only that bit is set to 1, everything else is set to 0. So something like this is pretty easy to do in a naive way with the loop, right? So if we want to write a program that is not very efficient, we can simply write a loop that iterates through all of the bits in this word, and once it finds a 0, then it, you know, sets the result, the bit in the return value to 1 at that position, and then returns, and that's it, right? But you know, the question is, can this be done more efficiently without a loop using some bit twiddling hacks, right? And sort of the idea is, so the idea that you might base your solution on is, the trick is basically that adding a 1 to a string of 1s turns the next 0 into a 1, right? So if you add, you know, 0, 0, 0, 1, 1, 1, you add 1 to that, you get 0, 0, 1, and then 3 zeros, right? So how can we devise an implementation of this based on this trick? Well, I mean, if you're really smart, then, and you think about it for a very long time, you might be able to figure it out, but it's much easier just to ask a synthesizer like Sketch to do that. So to specify this program in Sketch, so what you do is you actually implement the slow version, right? The one that we saw in the previous slide, which we called isolate 0. You simply implement that in Sketch. And then you say, okay, what I want to synthesize is this program isolate 0 fast, right? And then I say that it implements isolate 0, right? And this is how I say, well, isolate 0 is the reference implementation for this program, right? And then, well, what else do I have to say? Well, I have to say that this program is not allowed to use any loops, right? This program is supposed to just use a single, you know, bit twiddling expression. How do I do that? Well, the body of this function is simply this, you know, x per x3. So what is that? So this x per s3 is a sketch, right? So this is how you define your space of your space of candidate programs in Sketch. So I don't expect you to understand the details of this sketch, but essentially it's just describing it's describing the space of all bit vector expressions, which can only contain plus and exclusive or and bitwise negation, right? It cannot contain loops, right? So this is how we specify this synthesis problem in Sketch. So let me just show you how Sketch deals with it. So here I just have a Sketch file with, you know, exactly that same code that I just showed you. And if I run Sketch on that, we'll think for a little bit, and then it will return. So this last, this program that it returns for isolate 0 Sketch, right? It might be a little bit hard to read, but basically what it's doing is it invented this constant out S16, which basically just has a 1 in its rightmost bit and zeros otherwise, right? And the solution is simply to take the negation of the input and end it with this 1 plus x, right? So this is the solution Sketch synthesized for us. So this is basically the solution that that it came up with. So you might want to check that this indeed implements what we wanted, isolates the rightmost one bit in a word. Okay, so when is this way of providing specification suitable, the reference programs? So basically think about it whenever you want, you have some kind of translation tasks, right? So you basically want to, you have one program and you need a different program. So one case of that is something that's called super optimization, which is basically you just want to synthesize a faster program, right? But unlike regular optimization, where you're just doing little rule-based modifications here and there, you want to invent a completely different program. So you're doing it using search, right? And there are some really cool tools that do that using program synthesis. Another domain that has been really popular lately is something called verified lifting. So verified lifting, the idea is that you can lift code from, let's say, legacy languages and translate it into more modern, let's say, more high-level languages, more declarative languages also, which will make the code more maintainable or even make it run faster, right? Because this new language is really cool. So if you want to learn more about verified lifting, you can look at Alvin Cheng's work, for example, tools like QBS and Sting, which do verified lifting for database code and also for graphics code. So what's cool about reference programs? Well, they are programmer friendly, right? So if our target audience for our synthesizer is programmers, well, programmers can write programs, right? So that's great. And this is sort of as opposed to, let's say, formal logic, right? That not all programmers might be familiar with. But of course, it's not at the same level as examples, which are friendly even to beginners, even to non-programmers. Programs are really precise, right? So there's basically no ambiguity. We know exactly what the program should behave like. On the other hand, you know, this mode of specification is only applicable if there is some kind of simple program that we already have, right? And that's not always the case. Like, for example, if I wanted to use this mode of specification for something like flash fill, that just wouldn't be applicable. And another limitation is that to be able to figure out if our candidate program that we're synthesizing is correct, you have to basically check program equivalence, which is a hard problem. So checking correctness is much harder here than for examples. Okay, so this brings us to the third way of specifying intents, which is types. So here I will demo a tool that we have developed in my group called Google+. So the problem that we're going to look at, so let's say you're a Haskell programmer and you want to remove adjacent duplicates from a list, right? So for example, if you had a list like 1112221, you want to get the list 121. So as you can see, it doesn't remove all duplicates. So there can still be two different ones in this list, but they're not next to each other, right? So that's what you want to achieve. Okay, so, and let's say, I mean, you know that you can do that using, just by combining library functions together, but maybe you're not quite sure how to do this, right? So maybe you're not familiar with the standard library, or it's just like not a trivial task. So how would you, as a Haskell programmer, figure out how to solve this problem? Well, how would you even specify, you know, what you want to do to a synthesizer, right? The question is. So we draw inspiration from a very popular Haskell API search engine called Google, right? So what Google does is it searches for API functions by type. So if you're a Haskell programmer, you probably used it a bunch before. So for example, you can ask Google, what is a function that takes a function from A to B and a list of A's and produces a list of B's? And the Google will readily tell you, oh, it's a map function, right? So it's a map function that does exactly that. And that's great, Google is very popular. However, the problem is, what if there is no one library function that achieves exactly what you want, right? So in particular, so what happens if we ask Google for the type of that function we want to synthesize, the deduplicate function, right? So what is the Haskell type for this function? Well, we have a list of A's, right? So here A, think of it as a generic, right? So it's a type variable, means it can be a list with any element in it, and we are returning a list of the same A's. So it's not quite so easy in Haskell, because deduplicate will have to compare the elements for equality, right? Because we want to remove the elements that are equal. So you also have to tell, as part of the type, you also have to say that, well, those elements have to be equatable. For example, you cannot have a list of functions and then deduplicate that. So if you put this, if you figure out this type and put it into Google, though, you'll get some results, but basically none of these results are relevant. So this first function nub does remove duplicates, but it removes all the duplicates from a list. And that's because there's no single library function that does exactly what we want. So we figured out, okay, Google needs synthesis, right? So we want to be able to put library functions together. So we built this tool that if you give it the type for deduplicate and you give it a bunch of Haskell library functions, it gives you a ranked list of programs that you might want. So let me just show you the demo of that. So here's our interface to Google+. And like I said, we can just put that type that I just told you about right here and see what happens. So, Google Plus now starts returning some results to us. So let's look at these results, right? So for example, this very first one says, well, so you take your argument, right? So what you do is you call group on that argument, and then you call concat on that, right? And now, well, perhaps I'm not very familiar with what these functions even do, right? I don't know what this result even means. So I can, first thing I can do is I can hover over these components and get some documentation. So for example, now I learned that the group function takes a list and returns a list of, well, basically, it even has an example, right? So it basically groups the same elements together, right? It gets a list of lists where equal elements are grouped together, right? But then concat just concatenates a list of lists. So that's not really the function that we want. And we might be able to figure it out also from these usage examples that Google Plus gives us automatically, right? So it tells us, for example, that if we call this result on the list 1, we would get list 1 back, which is definitely not what we want, right? So we would want list 1 on that. And so using this automatically generated examples and the documentation, we might want to scroll through these results and see if there's anything that we like. Oh, this one looks really promising, right? So from 1, it gave us 1, from 0, it gave us 0. Let's see if, well, maybe it has more examples for us. Well, that maybe wasn't very useful, but I can also input my own example, like the one that I had on the slides, this one. And let's see what comes out. Yeah, that's exactly what I wanted, right? So this is probably what I want. So now I can also inspect it and see, so what did it do? Well, it first grouped similar elements together, and then it mapped the head function over those groups, right? Basically took the first element of each group, which is exactly what we want, right? So, and then I can just copy paste that into my code. So this is how you use types as your intent specification. But by the way, Google Plus, in Google Plus, you can also augment your specification with examples, right? It also allows you, if you think your type is a bit too ambiguous, you can also just put your example right here. And you can use it from the beginning using search, or if you just got a whole bunch of examples and you don't know which one you want and you're too lazy to look through them, you can refine the results that you already have, and it should come back in a second. I wonder why it does not. Okay, so it returned us this program that I picked for you earlier. Okay, so this is what Google Plus does. I wanted to show you just another example of using types as spec because, you know, since I like types so much. It's a different synthesizer that I developed called SyncWit. And I will demonstrate SyncWit on a similar problem, but sort of doing the opposite thing, right? So first we wanted to duplicate the list. Now let's say we want to duplicate every element in the list, right? And let's say here, we don't care if we want, if we do it using library functions, we are fine with doing it using recursion, right? So if we had a list like 1, 2, 3, what we want is 1, 1, 2, 2, 3, 3. So the idea behind SyncWit is that, well, if you just put in the type alone, right? So the type for this function in something like Haskell would be, well, I had a list of A's, and what I have at the end is still a list of A's, right? Because I simply duplicated every element. That would be very ambiguous, right? So it could return a whole bunch of uninteresting programs, like a program that just always returns an empty list. So the way Google Plus overcomes this ambiguity is using, so first of all, you can add examples, right? But also Google Plus has very smart semantic biases inside that it kind of manages to figure out which programs are very likely uninteresting and just doesn't return you these programs. But with SyncWit, I want to show you a different way to overcoming this ambiguity. And this is by giving more power to the types, right? So, because when I say types, there is a wide range of things that people mean by types, and some of them are more expressive and richer than others. So this is what SyncWit does. So in particular, SyncWit uses as its input something that's called refinement types. So what are these refinement types? So they're types decorated with simple logical predicates, right? So for example, if I just have type int and I decorate it with this predicate, this means that the value I'm describing has to be greater or equal than 0. So this, for example, describes a type of natural numbers, right? And by sprinkling these little predicates here and there inside our types, we can actually express non-trivial properties of our programs in sort of quite a programmer-friendly way. So we don't put too many annotations and we express pretty expressive properties. So here, so SyncWit takes those refinement types and takes a set of components from which to construct programs, and then automatically synthesizes a program from that. So let me show you how that works. So here is an online interface to SyncWit, right? And let's say we wanted to synthesize that, duplicate program. So I have to put in the type annotation for duplicate here. So if I just say I'm going from list of A to list of A, right? That's not going to give me the right result. That's probably going to give me something that just returns an empty list. But what I can do in SyncWit is I can tell it that the length of the output list has to be twice the length of the input. Right, so to do that, I'll have to name my argument, right? So I say this input list will be called X's, and this output list, I can say that the length of this list is equal to twice the length of X's, right? Let me put in some parentheses just for good measure. And then if I ask SyncWit to synthesize this program, right, it immediately synthesizes a recursive program that duplicates a list. So what this program does is it pattern matches on the input list. And if the input list is empty, it just returns the same empty list back. But if the input list is has a head and a tail, right? So it has a head element and a tail list, then it simply prepends this head twice to the recursive call of duplicate on the tail, right? Which is a recursive functional program to duplicate every element in the list. So, and basically what I want you to take out of that is that if you add just a little bit more power to these types, right, you can avoid a lot of ambiguity. And so this refinement types language, specification language can also specify much more complicated things, right? So you can, so I have actually examples right there. You can talk about, binary search trees and even red-leg trees and specify, things like negation normal form. But I see it as, very much like a pay-as-you-go kind of thing, right? So you can add very simple annotations, get a little bit of power, or add more complex annotations and get a lot of power. And also the programs that sync with synthesizes are provably correct with respect to those annotations on an unbounded set of inputs, which is something that you might worry about, right? So if you worry about program correctness. Okay, so to discuss the types as intent specification. So where would this be a good way to specify intent? Well, so one is this sort of, again, programmer's assistant kind of way of using synthesizers, in particular in the domain of API discovery, right? So if a programmer wants to solve a simple programming task by putting a bunch of library functions together, types could be a good way to specify that, right? So, and Google+ was an example of that. There's another tool called Sciped, which works similarly. Both of those tools actually also accept examples as additional specification because types are not always informative enough. And so we have sync-with that allows you to synthesize, full-blown recursive functional programs using refinement types. So what's good about types is they're relatively programmer friendly. For example, relative to, again, more formal logic, even more formal logic based specifications, because at least programmers in functional languages and in other languages with static types, they're used to using types. Types are very concise relative to examples. So sometimes you can express a lot more information in a more concise form. And type checking is usually designed to be automatic, right? So it's much easier to check program against a type than, for example, to check program equivalence, which we had to do in the previous case. And the cool thing about types is that they can actually express non-functional properties, right? So I have in particular some work on how to specify resource bounds, so some properties about program performance using types, as well as how to specify security properties using types. So you can specify those. And types are, type checking is really compositional, so it's easy to use it to guide the search. However, of course, there are limitations, and the thing, and the main thing is, if you use simple types, then they're still very ambiguous, right? That's why tools like Google+ and Sciped have to supplement them with examples. But if you're using advanced types like refinement types, well, then those require very special expertise, right? Not everyone is familiar with those. And then even if you do have that expertise, some properties are really hard to express and really hard to check and borderline impossible with these types. Okay, and finally, I really quickly touch on natural language, which is not at all my area of expertise, but there's some very exciting tools in this domain. So just recently at PL+HCI 20, there was a new tool presented in this domain called Regal that synthesizes regular expressions from natural language descriptions and examples, right? So for example, someone might say, I need a regular expression that validates decimal 18.3, which means that the maximum number of digits before the comma is 15 and the maximum number after the comma is 3, right? And then they supplement that with some positive examples of the strings that should be accepted and negative examples with the strings that should be rejected. And from that description, Regal synthesizes a regular expression for them automatically, right? And the idea of how this works is that usually you can use semantic parsing techniques to parse the natural language description to give you some kind of bias on the space of programs that you should consider. And then once you have the bias, you explore that space and, using the examples, and then you find the exact expression. So essentially, from the natural language description, you get a sketch that you get a rough shape of the program that you want, right? And then you use examples to refine that. And so natural language has been used to synthesize different kinds of queries, SQL queries, regular expressions, so in this tool, Sequelizer and Regal. And we have seen more and more of, natural language also getting into the programmer's assistant kind of space, right? So there was this tool from Microsoft, Synthesize What I Mean. And we have probably all seen this new GPT-3 demos where it synthesizes some Python programs from comments. I'm not sure where this will be going, but some exciting developments, definitely. So the good thing about natural language, again, it's extremely beginner friendly, right? Natural language is how we all communicate even before we launch a program. It's very expressive in the sense that there is no such thing that, so with refinement types, for example, if I have to talk about some complex math, I just can't, right? I just can't express it. With natural language, you can talk about whatever you want, right? The price you pay, of course, is the ambiguity, right? So natural language is extremely ambiguous. That's why it usually gets supplemented with other kinds of spec, like examples. And it's also very verbose. So sometimes, sometimes a couple of examples can really capture something that, a whole paragraph of text would need to describe. Okay, so this basically concludes the first part of the talk, where I was talking about specifying intent, right? So what I want you to take out of that is that synthesis is more than just examples and demonstrations, right? So there are other ways to specify intent. The best way to specify intent depends on both the target domain and the target audience, right? For example, if you're targeting programmers, we can use programs or types. If you're targeting beginners or end users, we can maybe have to stick with examples on natural language. And most importantly, these different methods of specifying intent are best when they are combined, right? So we have seen examples of how to combine types and examples in Hulu+, how to combine natural language and examples in Regal. And the cool thing is that they have different strengths and weaknesses, right? And that's why if they're used together, then they help sort of eliminate ambiguity by complementing each other's strengths. Okay, so this concludes the first part. And then the second part of the talk, I wanted to tell you a little bit more about how we actually do the search. How much time do I actually have left? Oh, 10 minutes. Okay, cool. So then I'll have to go through this really quickly. Yeah, I do have more material than I have time for, but that's okay. This is probably too low level for this school anyway. So so first of all, before we can talk about the search, I have to say a little bit about what the program space, how the program space is usually encoded, right? So in program synthesis, you usually specify this program space by giving some kind of a domain-specific language, right, or DSL. And the way these domain-specific languages are described is using some kind of a grammar, right? So I will use this example of a very simple list manipulating language. So which can be described by the following grammar, right? So we have list expressions in this language, which can be, sort a list, take a sub list of a list, concatenate two lists, singleton list, and an input variable X. And we also have integer expressions like find a particular number in a list, and also the number 0. And context-free grammars consists of terminals, which are basically the operations of our language, and non-terminals, where here we have two, list programs and integer programs, and they consist of productions that tell us basically how to build non-terminals from terminals and other non-terminals. So context-free grammars recursively define the structure of our language. And we have a starting non-terminal, which tells us, okay, the full programs that we're interested in are these list programs. So now the main challenge for search is, how do we systematically explore the space of all list programs described by this grammar, right, to find one that satisfies our specification. And so there are basically four popular classes of search strategies used in synthesis right now. Enumerative, then the second one is probably, if you're familiar with VSAs, you're familiar with this one. They usually, as a whole, they're called representation-based. Then there's stochastic and constraint-based techniques. And let me just give you a quick summary of these. So the idea of enumerative search is, just like it sounds. You will explicitly systematically enumerate programs from the grammar one by one and check if they satisfy the specification, right? And then the challenge there is to, how do you systematically enumerate all these programs from the grammar? And there are two main approaches to doing that that are known as bottom-up search and top-down search. Essentially, the idea of bottom-up search is you will start from the variables and literals in your language, like the X and the 0 here, and you will iteratively combine them into larger programs using these productions, right? So for example, how would we do that if, this is the language that we have, this language of list programs, and our synthesis task is given by this one input output example, right? From 1406, we want to get the output 14, right? So basically one way to solve this is to get a prefix of this list until the first 0. So in bottom-up search, we maintain something called a program bank. So in the very first iteration, we add programs of height 0 to this bank, our variables and literals like X and 0. And then in every next iteration, we'll basically take a production like sort L here, right? And now we have to fill in this non-terminal, this L, with everything that we already have in the bank of the right type, right? So with all possible list expressions. So here our only list expression was X, so we will do sort X, right? And then we'll do that for all of the other productions as well. So then at height 1, we'll get these programs, right? And then we'll continue like that. We'll do the same thing at height 0, and we so height 2, and we get a whole bunch of other programs, right? So as you can see, the size of this bank grows really fast with the height of the programs. But it so happens that we found the right program already at height 2, right? So if we take the sublist of this list from index 0 to the position of the first 0, then we'll get what we want. Okay, the opposite of that is what's called top-down enumeration. So here you start from the starting non-terminal, and then you expand the remaining non-terminals in your program using productions. So as opposed to having this bank of complete programs, in top-down search you have, it's like a work list algorithm. You have a work list, like a queue, where you have incomplete programs in there. So it starts with just having the starting non-terminal as the only program in the list. And in each iteration, we pop at the head of the queue, and then we fill in the very first non-terminal we see with all the possible productions, right? So we can replace L with X, or we can replace L with this other production, right? So, and we'll keep doing that in each iteration, popping something from the head of the queue and filling in all these productions. And so basically in our work list, we'll have a whole bunch of incomplete programs all the time. And then at some point, finally, we pop something from the front of the queue and we see, oh, this program is complete and it actually satisfies our example. So we found what we wanted. So both of these, you know, they scale very poorly with the size of the programs. So the key to making enumerative search work is two techniques. One is to prune or discard useless subprograms, and the other one is to prioritize the search, meaning explore more promising candidates first. And you know, I don't have time to go into this, but I'll just give you an intuition for why pruning works. Well, it's because when you're combining the bank of size n using some binary operation, right? So then at the next level, you will get sorry, using m different binary operations, you will get m times n squared programs on the next level, right? Whereas if you remove even one program from the previous level, right, you'll get m times n minus 1 squared. So there is a big reduction in the size of the bank at higher levels if you're able to remove even a little bit, even a very few programs at lower levels. And the idea behind prioritization is that, let's say if you have this work list of programs to work on, you know, some of them might seem more promising than others. For example, this very first program here looks like really dumb, right? Because it just has a singleton list and then we are getting, you know, some sublist of that. Whereas the second program looks more promising because we're getting sublist of our input list. And so we should work on that one first. So there's a whole bunch of techniques that do both this pruning and prioritization of programs in enumerative search. And sort of the pruning is based on two main ideas. First of all, that we can discard a program if it's equivalent to something we have already explored. For example, if we explored sort X, we don't want to explore sort of X because that's the same. And this set of techniques for doing that is called equivalence reduction. And another way of pruning the search is if you know that no matter what you combine this program with, there's no way to satisfy the specification. So for example, if one of your examples says that an empty list should map to an empty list, and then your incomplete program you're considering is something like singleton list with n in it plus some other list, then it doesn't matter what n is and it doesn't matter what L is, this program cannot possibly satisfy this example because we need to get an empty list and we will not get an empty list from this program. And this family of techniques for pruning are called top-down propagation, top-down specification propagation. So I'll skip over the my slides about equivalent programs. I guess my whole point was that there is a whole bunch of equivalent programs that we're generating during the search. And if we remove all of them, there'll be much fewer of them. Especially in programming by example, we actually only care about whether programs are equivalent on the inputs that we're given. And so if we use that definition of equivalence, we can prove even more programs. So those will be the only programs that we're left with. So for prioritization, there's also some very exciting techniques out there that are essentially learning that are learning the weights of the different productions from a corpus of code and then guiding the search using the weights of the productions learned from the code. And you know, you can so there's this exciting work on Euphony published in 2015 that does that, but I'm not going to go into details on that. So just to wrap up about enumerative search, right, so there are these two main ways of doing that. The bottom-up search, which basically is the dynamic programming algorithm, which is great because it gives you a lot of caching, and so that makes it efficient. And it's very good fit for equivalence reduction because you can evaluate candidates because all your candidates are complete programs. On the other hand, top-down search has sort of the opposite set of advantages and disadvantages. It's goal-directed it's good for this top-down specification propagation, and it also can be guided with more precise learned weights. Some examples of enumerative synthesizers that I have mentioned before are Synquid, Morpheus, and Snippy. And good thing about enumerative search is that it's very flexible. It works for any language you want as long as you can evaluate this language. But on the other hand, it might not fully leverage the specification of the DSL. So VSAs are probably something that you're familiar with. The idea here is to build an explicit compact representation of the set of all programs that satisfy the specification. Examples of tools that work using VSAs or representation-based search are FlashFill, FlashExtract, WebRelate. So all I wanted to say about that is that representation-based search is very efficient when you can apply it, right? And it's in particularly, it's very good at returning a ranked list of solutions and not only the first solution, but it's very restricted to a particular class of DSLs. So basically when it works well, but it doesn't work in too many cases. Okay, so quickly about the two other remaining search strategies. So stochastic search. So when is stochastic search good? So it depends on what your search space looks like. So if you think that it's likely that you will find your solution in as a small program, you should use enumerative search. If you know which productions are likely, you can use weighted enumerative search. But if you sort of don't a priori know the distribution of your search space, you can use the stochastic or local search, where basically the idea is, well, you have some fitness function that describes which programs are likely good or bad, right? So this would be a program, and this would be a better program, you know, denoted with the darker color on this picture. And you just start from some random program and you mutate it, right? So those edges represent, you can mutate the program P1 into P2, and then you simply do this sort of random walk through that space, trying to find, you know, your optimal program, like this very dark program right here. And but unfortunately, if you simply always only go to the next program if it's better than the program that you currently have, you'll get stuck in the local minimal, right? So the way these techniques do that is they use techniques like Markov chain Monte Carlo sampling, right, where they introduce randomness, where even if the next program is worse than the one that you currently have, you still have some probability of picking that program. And this probability should decrease with depending on the difference between how good those programs are, right? So, and what these techniques are able to achieve is actually pretty impressive. So they have been used, for example, for super optimization, and they can, let's say, as an input, you're given this big assembly program on the left, and then a tool like Stoke that uses MCMC sampling is able to generate an equivalent program that is much, much shorter and much, much more efficient than the input. Examples of tools that use stochastic search are tools like Stoke that I just mentioned, and Frangel that I mentioned before in the talk. The cool thing about stochastic search is that they can explore program spaces with no a priori bias. So they can explore even like large programs, right, which enumerative search cannot do. But of course, they're not exploring them systematically, right? They're exploring them in this stochastic fashion. And so these techniques are also good when you have some kind of distribution, you want to sample programs according to that distribution, and it's hard to do in a systematic way. But the big limitation of the stochastic techniques is that you always need some kind of cost function. You always need to be able to tell whether the one program is better or worse than the other, right? And for this technique to work, you need this cost function to correlate with, to approximate correctness. And so if we always had a cost function that that faithfully approximates correctness, you know, then synthesis would be actually a much easier problem, right? Because we could just incrementally update, incrementally sort of do the hill climbing in the space and find the right program.
Okay, Nadia, I'm gonna pause you there. I know constraint based is another really good search strategy, but I want to make sure that everyone here gets a chance to discuss and ask you lots of great questions, because you've presented so much, and we're drinking from the fire hose. Can I stop you there?
Sure. I just then I'll just go to, oh, sorry. Perhaps it would be good to finish at this slide where it shows just the overview of the 4 different search strategies that I talked about, right? So I think that the takeaway from here, and just to say, you know, one sentence about constraint-based is the idea of constraint-based is that you encode your synthesis problem as a constraint solving problem and just use a SAT solver to deal with it, right? And so the thing to learn from it is that constraint-based and VSAs are very efficient, but less flexible in the sense that not every synthesis problem can be encoded can be encoded in using these search strategies. On the other hand, stochastic and enumerative, you know, are more flexible. They're suitable for more languages, more kinds of specifications, but as you know, you pay for it in efficiency. And that is basically what I wanted to talk to you about today. Thanks.
Awesome, thank you. What a tour de force. You had, Hila and I gave you a very difficult assignment of essentially covering a vast amount. And I love the call out of kind of both the overview and how you went into each of these components and what pros and cons they have. So I'm going to ask everyone to, on Sriram's invitation, join breakout groups, max 10 minutes, probably a little bit less, and then we will regroup and ask Nadia our curated questions. All right, I see the first hand up. Remember that in order for everyone to get their questions answered, the more concise you are, the better off we all are. And it gives Nadia more time to answer your question as well. Chris Martins, why don't you go ahead?
Sure. Hey, Nadia, good to see you. I was wondering about, you mentioned some search strategies that include heuristics, and I was just wondering if you could say a little bit more about what kinds of heuristics those are, if you have criteria like admissibility, consistency, like you might have in other settings, that kind of thing.
Oh, you mean when I was talking about the prioritization? Which
yeah, prioritization and pruning, but yeah, mostly prioritization.
Oh, okay. So when I talk about pruning, those are usually not heuristics in the sense that when we prune something, we want to be absolutely sure that we cannot find the program in that space, right? So usually the techniques that are used for pruning are logic-based techniques that, you know, using verification to figure that out. So for prioritization, it's sort of the, those are the more approximate techniques in the sense, right? So that we just, we don't completely rule out a branch of search, but we prioritize them. And so for the work that I was mentioning, the work on euphony, right? So there the search is guided by the combination of sort of weights in your grammar that are learned from a corpus of code. So there's also recent work, including by us, but also work on the tool Frangel that I mentioned, that are able to learn some of these weights online while doing search, right? So which is also very exciting. The way euphony does this prioritization, it uses the A-star algorithm, which means that they do need a heuristic, which is probably why you mentioned that. So A-star algorithm needs a heuristic to figure out, you know, how far possibly can it take to get to a complete program, right? So they actually use an admissible heuristic for that, and you can find it in their papers. So they actually prove. So basically, the idea there is like, if you don't take the context of this production into account. How many unrollings of this non-terminal can it possibly take to get to a complete program? And this gives us an admissible heuristic on the distance to the next complete program.
Okay, nice, thank you.
David Moon, go ahead.
Hey Nadia. So I was, you know, with program synthesis, I'm always like wondering, okay, so what happens if it goes wrong? You know, like you want to be able to, you know, somehow fix what went wrong. And so maybe you would expose the underlying synthesized program and allow the user to tweak it. And that works great for programmers, but I'm wondering for like end users, like I guess I'm curious like about like if you have any insights on like the design of effective DSLs for end users so that you know they can retain control over the like the ability to go back and edit and like sort of get something that they want.
Yeah, this is a great question. I don't think I have a definitive answer on that. I think it's a really good research question and research topic to explore, right? So, I mean, one thing that we did work a little bit about is on helping programmers comprehend the results of synthesis, right? So this I have shown you as part of the Google Plus project, right? So we're generating these automatically generating inputs to demonstrate the behavior of the synthesized programs, right? So in Hila's work as well, she worked on, you know, what are the best ways to show the programmers like these intermediate values to help them understand the program. So I think this can partly mitigate the challenge of, you know, users not understanding the program. So this is more like in a setting, not when you're an end user, but maybe you're a programmer, but you're not familiar with the language, you're not familiar with the library. These kind of techniques can help, right? So how do we present programs to end users in a way that they can edit them? I think this is a really great question. So I think also that there's a whole bunch of techniques on sort of more active learning for synthesis, right? Where there are techniques that if they know that the spec is ambiguous and there's more than one program that satisfies the spec, they ask the user additional questions, right? There was another paper presented at PL+HCI as well on that, right? So how to ask the user optimal questions. So this could be another route to allow the user to influence the program without them having to edit the code directly. But yeah, I think, you know, we don't have all the answers here for sure. Great question.
Thanks.
Daniel Wang, go ahead.
Oh, yeah. Thank you so much for the amazing talk. We got a really good view of the work done around the PL side of program synthesis. So I was wondering, what are some promising areas where the HCI side could add to the field?
Yeah, thanks, Daniel. I'm not sure I'm the right person to ask that because I am on the PL side. So I did mention some of the works I mentioned were from the HCI side. So for example, the Rex work for PBE for data scientists came from the HCI side. Yeah, but perhaps I am not the best person to answer.
If you're uncomfortable answering that question, we can shelve that for the panel. But it is a great question.
Yeah, definitely a great question.
Payush, go ahead.
Hi, Nadia. Thanks for the talk. In our group, we discussed how synthesis is easier for smaller languages. And in some languages like Clojure, it's natural to define a DSL around your problem domain. So is there any research on usability of synthesis for DSLs?
Oh, interesting question. So I would say all synthesis is with DSLs in some way, right? So because even if you're using like a larger language that is not formally a DSL, you're restricting your search space in some way, making your language a DSL. So I think the interesting, but I think you're raising a very interesting point that some languages are just meant for, you know, defining DSLs, right? Like Racket as well, for example. So whether there's some really good possibility there to mesh up, you know, those DSLs that are really easy for programmers to define and synthesis. I think it's a great question. I actually know of any work, at least nothing off the top of my head that explores this connection, but I think that would be a really cool connection to explore.
Thank you.
Josh Pollack, why don't you go ahead?
Hi, Nadia. Thanks for the talk. In our group, we're sort of discussing this idea that it seems like from a tool perspective, providing both high-level specifications and examples seems to improve the fidelity of synthesized programs. But from the HCI perspective, users often find specifications hard to write. And I think, Elena's group has published a little work recently, for example, on interactively abstracting examples in the space of DFAs, but we were wondering if you had some other thoughts about ways that you can help users write these high-level specifications in Google+ or Synquid.
Oh yeah, really good question. So first of all, I think I'd like to comment that what we found, at least in the user study that we did with Google+, is that if you give users multiple modes of specification, right, that's always a positive, because they would just use the one that they prefer and the one that is best for this particular problem, so it's kind of a win-win situation. So if you're thinking about, adding formal specifications, examples, types, natural language to your tool, I would probably say yes, just do it and then see what the users actually end up using. And then, of course, there's a whole bunch of challenges there in how to actually combine all these different specifications together during the search so that you can leverage all of them during the search. So as to how to help users write formal specifications, this is a great question. So there can be multiple approaches to this problem, right? So for example, again, in Google+ world, right? So what we found is that Haskell beginners, they actually have trouble coming up with types sometimes, right? So if types are complicated, if they're higher order, they have these type class constraints, which is the thing that I showed you with the EQ. So Google+ actually also has the mode where you just specify examples and then the types are inferred from those, right? So this is one route where you can go, where you have multiple specification modes. You can try to help users to go from one to another. Right, but then I also believe that, if you should choose specifications that are of this more pay-as-you-go style, right? So hopefully you'll just, get the programmers in with some, really simple kinds of specifications, and then they get a taste of it, and then they just, learn them, and then they want more.
What you've described is also referred to as scaffolding, where you provide something that is accessible, but you also help scaffold them if they want to start using more and more complex forms of specifications. Yeah. So if anyone wants to think more about that, that's a good keyword to search for.
Oh yeah, great. Yeah, it's great that you put some more scientific terms on my ramblings.
just not more scientific, just a different discipline, more jargon. Noel Welsh, go ahead.
Thanks for the great talk. Our group was interested in combining machine learning and program synthesis techniques. So perhaps you could talk about the benefits and drawbacks of mixing more machine learning techniques into program synthesis.
Yeah, great question. And this is definitely a very hot topic these days, right? So I think what happened in this area is that first, the neural nets people, they came in and they started working on this, neural programming kind of stuff, where the goal was to replace programs altogether with neural nets, right? And that didn't really go well for various reasons. And, one of the reasons being that programs are good because they're interpretable, right? So we want to generate programs that people can read, that people can edit, and that we know what's going on in there and that we can verify. So I think a much more promising trend in my view is really what you mentioned, combining machine learning and program synthesis. So in this domain, most of the recent work is about, how to train some kind of statistical model of your language that can be used to guide search, right? So the thing that I mentioned very briefly about weighted enumerative search is an example of that, right? So you can learn various fancy statistical models that can either capture just, what natural programs in this language look like, or they can try to capture the connection between the specification in the program, right? So conditioned on the specification, what is the more likely program? And yeah, and then, so one challenge is how do you learn those statistical models? The other challenge is how do you use them to actually guide your search? But I think there's great progress in both of those recently.
The final raised hand that we have is from Will Crichton. Go ahead. Oops.
And now I'm unmuted. Perfect. Our question was, we were wondering about what programs do programmers most need synthesized? And so an HCI way of asking that is, how do we do need finding in this space? And that seems challenging to us because if you just ask a person, what do you need synthesized? That depends on how you define synthesis. Like if they just say, read my mind and turn it into a program, that's obviously not tractable. And so we were curious how you decide what tasks and application domains to work on within synthesis.
It's an excellent question. And I think the PL community is still struggling a little bit with that, right? Because there is this two sides, right? What the programmers need and what we can do. And because what we can do is so restricted that we tend to, just go with what we can't do without regard for, what the programs actually need. But I think in recent years, we've been really, working on bridging this gap, and I'm really excited about that. So I think the domains that I mentioned in the talk are like good examples of domains that we found where, those two things really fit, right? So like I said, it's usually either some very restricted domain specific, languages like SQL, like regexes, like the string transformations in Excel, right? Where there's a combination of the language being restricted enough and domain being restricted enough that we can leverage that to do synthesis, but also it being really popular with end users, and really confusing to write those things by themselves. So I think definitely data science is like a big domain right now, and everyone is trying to do something for data scientists, help them clean their data, help them transform their data. I think this is great because this is sort of in between complete end users and professional programmers, right? So there's a rich space of interactions that would fit data scientists, and also the domain is again restricted enough so that we can do something about it. So I think Hila and I are particularly excited about helping professional programmers as well. And there, there's a question of what they would need help with. So as I mentioned in my talk, that the one thing that I envision is sort of like, how do we automate Stack Overflow, right? So obviously that's something that programmers need because they do go on Stack Overflow and they do ask questions like, how do I parse this file line by line, or how do I convert a byte string into an integer, or whatnot, right? And they usually specify it using natural language and examples and, perhaps types as well. But then they have to wait a couple of days for the answer, right? So if we could just make a tool that takes this kind of description and gives them the snippet back, I think that would be great. So beyond that, another thing that I'm interested in is, instead of just generating code sort of from scratch, from an end-to-end specification, how do we integrate program written code and synthesized code in sort of in more interesting ways? So for example, I have this paper that's coming out at ICFP on using synthesis to generate policy enforcing code in applications that manipulate sensitive data, right? So in this case, the programmer writes their application logic in their regular programming language, just as they would. And on this side, they write declarative security policies, like, for example, it's a double-blind conference. So a reviewer is not supposed to see authors' names, right? Things like that. And then the synthesizer goes in and inserts and synthesizes these little checks inside the code that enforce the policy, that provably enforce the policies. So that's sort of, I think, another promising domains where we don't have to synthesize code from scratch, but we sort of use it to integrate cross-cutting concerns into the code. But you know, beyond that, I do believe we need those need-finding studies to figure out what the programmers really want. And you know, I hope you guys will do more of those.
Well,
Thank you.
thank you so much, Nadia. I know we have one more hand, but I'm being encouraged to give everyone a break before we regroup for the panel. So I'm hoping that Zanzi, you will raise your hand again for the panel. Nadia, it's been an absolute pleasure, and thank you for helping me drink from the fire hose again.
Thanks for inviting me. So happy to be here.